All right, let's take a look. Okay, so there was an overwhelming response for D, okay, and right off the back, D is not the right answer, but let's take a look at the question. So which of the following is not one of the three barriers that the filtrate must cross before entering the Bowman's capsule? So it's really also asking, what are the three layers of the filtration membrane, right? And so it's going to be the capillary endothelial cell layer that has an associated basement membrane. So the basement membrane is a layer that that filtrate will have to cross. It also has to cross the surrounding epithelial cell layer. And we're talking about those podocytes. Those are the cells that we're talking about that make up that epithelial layer, which is really a part of the visceral layer of the Bowman's capsule. So the three layers we're going to go across are the capillary endothelial layer, its associated basement membrane. Remember, endothelial cells have that underlying basement membrane. And then we have the epithelial layer of the Bowman's capsule. It's not going to go through the apical membrane of the tubular cells because we're not in the tubular structures just yet, okay? And I just want to go back here to kind of illustrate that. Where was it? Okay, it may have been back in the anatomy slide. Yeah, but let's sort of illustrate it on this slide. So we're going across this membrane here. So it's the endothelial cell. Here we go. So we're going across the endothelial cell here, the associated basement membrane of that endothelial cell, of that endothelial lining, and then the epithelial cell, which is the podocyte, okay, the foot process of the visceral layer of the Bowman's capsule, okay. When we talk about the tubular cells, we're talking about this region of the nephron. So we're not in the proximal tubular region. We're not there yet. And the filtrate doesn't have to cross these cells. Even when we do get here, the filtrate is not crossing these cells. It's just moving along the tubule. So we really want to make that distinction that we're going across the three layers of the filtration membrane and not across the tubular cells. That's an entirely different process. That's going to be the absorption that we'll talk about going forward. Okay. All right, so the answer here would have been C. This is not a part of the filtration membrane, the apical membrane of the tubular cells. Let's look at another question. All right, last 5 seconds. Okay, let's end here. A lot of response for B. What is the movement? Sorry. What is the movement of filtered solutes and water from the lumen of the tubules to the plasma fluid compartment called? Okay, and D is correct. This is reabsorption. So we're reclaiming substances from the filtrate, which is in the lumen of our tubular structures of the nephron, and we're moving those back into the plasma via the connection with the peritubular capillaries or the vasa recta, depending on where we are in the tubule, and that is reabsorption. Okay. All right. Okay, so that's it in terms of practice questions there. Let's go ahead and get into where we left off, which was the glomerular filtration, really getting into the details of this process. And we introduced this idea that Starling forces are at play here. And we started out last time by just describing those Starling forces. And just to do that again here in a general sense, we want to think about the hydrostatic forces as being caused by the presence of fluid in that space. Remember, hydrostatic, hydro meaning water, a force that is created because of fluid present in a space. And so we have hydrostatic forces in the glomerular capillary that is pushing fluid out into the Bowman space. We've also got hydrostatic forces present in the Bowman's capsule or the Bowman space that's pushing fluid back into the glomerular capillary. And remember, hydrostatic forces are push forces. The other force generally is the osmotic or oncotic force. And this is a pull force. And again, going into the reason for this force, the underlying mechanism here, this is due to the presence of immovable solutes or impermeant solutes, mainly the proteins that are present in the capillary. So while we have proteins present in our glomerular capillary that's present in the plasma, we will have an oncotic force pulling fluid back into our glomerular capillary. But because these proteins cannot cross this membrane because of their size, while we want to acknowledge that there is a force, right, we want to appreciate that it is also zero. The idea that there are no proteins present in the Bowman's capsule, and so the oncotic pressure in the Bowman's capsule should always be zero, okay? And I'll talk about some instances where we do have injury to the glomerulus and we do see movement of these proteins over, but then that is not normal, right? That's going to be completely abnormal and pathologic. So let's go through these forces here again more individually. So the glomerular capillary hydrostatic pressure, this is about 60 millimeters of mercury. So it's really strong, really high. There's a lot of fluid in our capillary, and it's due to the resistance of the efferent arteriole. So the efferent arteriole, and that's kind of being illustrated here, usually has a wider lumen. It usually has less resistance. And so the afferent that's coming in has a smaller lumen that's being tightly regulated, whereas the efferent usually has a little bit of a larger lumen, and so we see a lot of that pressure coming in. The Bowman's capsule oncotic pressure is going to be our second force. Again, this should always be zero. It's due to the lack of proteins in the filtrate, so there's no proteins crossing this, this filtration membrane. Therefore, the oncotic pressure over in the Bowman space should always be zero. And then getting on to our opposing forces. So just to kind of recap here, these two forces we just described favor filtration, that strong glomerular capillary hydrostatic pressure and that weaker or zero, excuse me, Bowman's capsule oncotic pressure. So those forces favor filtration. In other words, the movement of fluid from the capillary over into the Bowman's capsule. The forces that oppose filtration are going to be the other two remaining forces. So the Bowman's capsule hydrostatic pressure, which is 15 millimeters of mercury. And now this is relatively high if we compare this to our systemic capillaries. If we think about the interstitial fluid, hydrostatic pressure, there wasn't much fluid over in our interstitial space, and so we had a very small number for our interstitial fluid, hydrostatic pressure. Here we're seeing something different. There's a little bit more fluid present in our Bowman's capsule, and so we see a stronger force sort of opposing filtration because of the presence of more fluid that's actually being filtered out more rapidly. And then lastly here, our second force that is opposing filtration is about 29 millimeters of mercury. This is our glomerular oncotic pressure. This is higher again than we see in systemic capillaries due to the presence of plasma proteins in a smaller volume. So there's less of a volume present here in terms of the surface, that is seen in this glomerular capillary, but there's more proteins proportionally present, and so we have a higher glomerular oncotic pressure, right? And again, that is a pull force exerted by the proteins that cannot otherwise cross that membrane. Okay. So this is just looking at, just to summarize this, and we'll illustrate this out here in a bit, but just thinking about the direction of our forces, right? Going from the glomerulus over into the Bowman's capsule, and thinking about our two favors that favor filtration, our glomerular capillary hydrostatic pressure pushing fluid out, our Bowman's space oncotic pressure pulling fluid in, which again is usually or should be zero. And then our forces that are opposing filtration rather, because it's not favoring absorption here the way that it is in the capillaries. It's actually opposing filtration. That's going to be our Bowman's capsule hydrostatic pressure, which is pushing fluid back into the glomerular capillary, and then our glomerular capillary oncotic pressure, the presence of the proteins here, largely in terms of the proportion there, pulling fluid back in that direction. Okay, so let's spend a little bit of time sort of illustrating this and practicing this. So just like we did in the capillaries, you should be comfortable doing calculations, so looking at different values and making analysis about the different values, and also just calculating the overall glomerular filtration pressure. Okay. And so while we know that filtration is the overall movement of fluid, the net movement of fluid, we still want to be able to prove that, so that's what we're going to do here. Okay, and so let's remind ourselves of the anatomy here. So we have our afferent arteriole, our efferent arteriole, and then we've got our ball of capillaries. I probably should have drawn that in red because they're vessels, but I think we get the idea. So we have our ball or tuft of capillaries. And then we have our Bowman's capsule. Okay. And so thinking about our forces here, we have our first force, which is our glomerular capillary hydrostatic pressure. That's moving in this direction. So our glomerular capillary hydrostatic pressure. Let's actually just make a little key up here. So this is a push force, and it is favoring filtration. Okay. We've also got our Bowman's capsule hydrostatic pressure. So it's going to be moving in the opposite direction. Our Bowman's capsule hydrostatic pressure. Okay. This is going to be a push force also, but this one is opposing filtration. Remember, this is from a different space. Although they're both push forces, one is pushing fluid out, one is pushing fluid back into the capillary. So while it's also a push force, this is opposing filtration. Okay, let's look at our oncotic forces. Let's use another color here. Okay. So first we have our Bowman's capsule oncotic pressure. Right, so this is going to be moving in this direction. So our Bowman's capsule oncotic pressure. Now we know that these are pull forces or osmotic forces. And this one is going to be facing filtration because we're in the Bowman space, pulling fluid from the glomerular capillary. So this one favors filtration also. And then lastly, we have, let's put a note here that this should be 0. Okay, really important to make that note there. Let's see, question. Someone's asking if a force is opposing filtration, would it be a force of absorption? So we're not going to think of it as being absorption because we know that the overall net movement of fluid is out into the capillary. And so it's just opposing filtration, but you can associate it with absorption if you're thinking back in terms of comparing it to what happens in the capillary bed. But while we have forces trying to move the fluid in different directions, we know that the overall net direction is always moving fluid out into the Bowman's capsule. So it would be incorrect to think about this as absorption because that doesn't actually ever happen. Okay, but in theory, it is a force that would favor absorption. Okay, great question. All right, so our Bowman's capsule oncotic pressure, we said, is also a pull force favoring filtration, but this should always be zero, right? Zero proteins present in our Bowman's space. And then our last force, which is our second oncotic force, is the glomerular capillary oncotic force, which should be going in that direction, right? The presence of proteins in the capillary, pulling fluid back in that direction, and this would oppose filtration. Okay, so our glomerular capillary oncotic pressure, also a pull force, but opposing filtration. Okay. All right. Let's add some values here to our numbers and let's try to, let's calculate this in an attempt to prove that what we said is just true, that it's always net filtration taking place, okay? So let's put some values here. So let's say our glomerular capillary hydrostatic pressure was 60, which we know it should be. Our Bowman's capsule hydrostatic pressure is 15 millimeters of mercury. And then our glomerular capillary osmotic pressure or oncotic pressure is 29 millimeters of mercury. And lastly, our Bowman's capsule oncotic pressure is 0 millimeters of mercury, okay? And so we're going to plug in the same equation that we did for our net filtration across the capillary bed, but here we're going to call it a different term. This is called the glomerular filtration pressure. All right, and so we're looking at our same equation. So the glomerular filtration pressure is equal to our filtration forces minus our forces that oppose filtration. Okay. And so just plugging in, this is why it's so important to really zero in on which forces are favoring filtration and which are not, okay? So that we can sort of plug this in with a little bit more ease. So our forces that favor filtration, we know are our glomerular capillary hydrostatic pressure. So we're gonna plug 60 here. We're also gonna add our second filtration force, which is our Bowman's capsule oncotic pressure, which is 0, so 60 plus 0. And then we think about our forces that are opposing filtration. So we're starting with our Bowman's capsule hydrostatic pressure, 15 millimeters of mercury. And we add our glomerular capillary oncotic pressure, 29 millimeters of mercury. Let's just put 29, okay? And so just doing some math here, we're gonna have 60 on this end, minus 15 plus 29, which is 44, okay? And so right away, without really even doing the math here, we know that the filtration forces are bigger. So right away, we know this favors filtration. But then even just doing this math, 60 minus 44, this gives us 16 millimeters of mercury. And because this is a positive value, we also know that we're favoring filtration.